Okay, let's make a start. Okay, so so last time we just started off looking at, phasor description, okay? And, so the phasor representation of a vector field, okay? A bit like we have phasor representation of, voltages and stuff in circuit theory, okay? So, the actual real vector field, which depends on position and time, okay? And also is a vector, so it has a direction as well, okay? And, it's the real part of, this phasor representation, which is function of position and a particular frequency omega times e to the j omega t, okay? Now, this positional part, this phasor here, this phasor representation, which is function of position and omega, we can actually further represent that as, a vector, a constant vector, okay, which has amplitude and direction, which is, just a function of omega, okay, and this e to the j k dot r, okay, so this is giving the position, the spatial information, okay, how that phasor changes with position r, okay. For the moment, we just say, k is real, okay, so k vector equals k x in the ax unit vector direction and ky kz, okay. So if we want to find the real vector as a position of r, which is x, y, and z, time, then it's the real part of this, okay, and we can combine those because it's two exponentials multiplied by each other, okay, and when we take the real part of that, it's going to be a cos, right? So it's this x naught omega times cos omega t minus k dot r, okay. I'm going to show later that corresponds to an unattenuated plane wave travelling in the unit direction given by k divided by the square root of k dot k, right? Okay, so and these are some examples, I think, okay, plane wave function. We also let this k be complex, okay, so then we've got two parts. We've got a kr, which is the real part of k, and ki, which is a real number as well, so this is a real number, and this is a real number. We put them together as kr minus jki, okay, to give k, which is a complex number, okay. And we go through that process again, and when we look at the real, in this case we're looking at e, okay. When we look at the actual e as position of r and t, or this vector e as position of r and t, then it's going to be this e naught, which is a function of omega, times e to the minus k dot r, okay, cos omega t minus kr, this is ki dot r, minus times cos omega t minus kr dot r, okay. So that represents an attenuation, okay. So it's going to be, if ki is positive, then it will represent an attenuation as you're going in some direction. So if r increases, okay. Well, if ki dot r increases, okay, so the vector has a direction, okay. So if you're going in the k hat direction, then it'll be represent attenuation. If it's a negative sign, then it might represent gain or increasing. Okay, depends on the direction. Okay, so it depends on the medium and the direction. And we generally here we're going to assume that the real imaginary parts are collinear. Okay, so this k is going to be kr minus jki in the k hat direction, the unit vector in the k direction. Okay, and then it's given by this. Okay, so we have some attenuation, and we have this thing which is changing the phase of the field. Okay, that's just going through that again. Okay, so I want to understand what this description. So there's when we represent the field as something like this, okay, as a phasor with this e to the j k dot r as the spatial, how it varies spatially. What does that mean? Okay, well, we can see that the amplitude of the field, so this is going to be the amplitude, how the amplitude varies as a position in space. It's constant over a surface defined by k hat dot r equals a, where a is some constant. Okay, so if this is constant, k hat dot r is constant, then this will be a constant, and so this will be a constant. So the magnitude of e is going to be constant. Okay, just the phase will change with time and position. Okay, so let's look at that. So if we take a vector r naught, which is in the k hat direction, okay, so we go r naught's in this k, the unit vector k of k direction, k hat, okay, then we can define all these other vectors r, we'll define them by taking a vector d, okay, at the point r naught, okay, which is perpendicular to the k hat direction, okay, perpendicular, okay, so any d, okay, so it can go around all over the place, okay, so that's defining a plane, okay, so you've got the vector r naught, which is in the k unit vector direction, okay, and then if we've got this d that's perpendicular to that, okay, and d can be any length, okay, in lots of directions, but it's got to be perpendicular to r naught, okay, so that's going to define all these r's with this locus. So we want to see what is the form of the locus described by k dot r, right, the locus of points. So remember in maths you have a locus set of points that satisfies the equation, okay, k dot r equals a constant. So anyway, so this r is defined at the end of this d, and this d can be moving around and also any value. So that actually defines a plane, okay? A plane that's perpendicular to the unit k direction, okay? The unit vector in the k direction, okay? That's what it's defining, okay? So we know that k dot d has to be equal to 0, right? Okay? And we know that any r that's in that plane is given as, r naught plus d, right? Okay? So r minus r naught equals d, okay? So k dot d is equal to k dot product with r minus r naught, okay? And that has to be equal to 0, right? Yeah. So Pythagoras. So it's just a right triangle, right? So this is at 90 degrees. Okay. So r equals r naught plus the vector, so plus d. Okay. Well, they're at 90 degrees, but so just addition of vectors, right? Give r. Okay. So k dot d is 0. So therefore, k dot r minus r naught is 0, right? So it means that k dot r has to equal k dot r naught has to equal a constant. Okay, is this clear? So and r naught equals k hat in the r naught direction. Okay. So so it's just a fixed distance. Okay, r naught, magnitude of r naught, right? Yeah, because it's perpendicular to each other. It's at 90 degrees, right? So you've chosen d to be at 90 degrees. So r naught is in the direction of k hat, and the unit vector of k, and then d is at 90 degrees to that. So the dot product is going to be 0, right? So it's saying that for any of the points in that plane, okay, for all points defined by this plane, okay, this is going to be a constant, clear? So k dot r is going to equal a constant. So that says that the amplitude of the field is constant over this plane, okay. And we do a similar argument for the phase. So the phase of that is omega t minus k r, k hat dot r, okay, it equals some constant phi naught, okay. And so say we're choosing a time t naught at a particular time, okay, and this k hat dot r is going to be omega t naught minus phi naught divided by k r, right? It's going to be a constant, okay, at a particular time. Again, from the same arguments that we had before by defining r to be a plane perpendicular to this k hat, okay, we can see that this defines a plane of constant phase, okay. So this is showing that at a plane perpendicular to k hat or unit direction of the k vector, you're going to have constant phase, okay, constant amplitude and constant phase, okay. So these planar surfaces represent wave fronts going along, okay, wave fronts, and the amplitude and the phase of that wave are constant over that plane, okay, perpendicular to k, okay. So the called a uniform plane wave. That's conceptually tricky, but I hope you can visualise that a bit now. Okay, so we're going to look at seeing that those planar waves, particular origin, can be anything, right? So we're looking at r. We're just saying we choose an r naught, which is a vector, which is in the direction of this plane wave. Actually, it turns out that this k is the propagation direction, okay. We choose that vector r naught, okay, in the propagation direction, and then we're defining plane perpendicular to that r naught, which is perpendicular to the direction of this k, okay. And and see in any plane for any r naught, there's constant phase and constant amplitude. So these are like plane waves that are propagating through space, okay. And we're going to show that they're solutions to Maxwell's equation in the isotropic media, and particularly when we talk about no independent sources in space and no boundaries in this space, okay. So just some identities. Okay, so this is what E, the real field, is, and it's the real part of the phasor description times e to j omega t. Okay, it's for the E field. Okay, so and where this phasor is given by this E naught, which is a vector, can be a function of omega, and this is the spatial information given by spatial variation given e to the j minus j k dot r. Right? Okay. So we can take the temporal derivative of the phasor, okay, of this, and it's just j omega e to j omega t. Right? Okay, so temporal derivative and spatial derivative. Okay, you can put the definitions of talking about here the gradient, the Laplacian, the divergence, and the curl, from Cartesian coordinates into this. Okay, and you can see that if you work through that, the actual results are this. Okay, are these results? Okay, you can work through that if you really want to. Okay, but and they're given in your formula sheet. Okay, so a bit like the temporal derivatives. When we take the spatial derivatives, we also get solutions, or when we take the spatial derivatives, we get some result which is basically k in some way multiplied, or a dot or cross product with the original vector itself. Right? Okay, you should be fairly intuitive because exponents, when you take any derivative of them, then it's just the exponent, the actual function at times what was in the in the exponent. Okay. So anyway, that if you can work through that, I'm not sure if you did that in the first vector calculus, might be exercises or something in the initial prac class on vector calculus revision. Yeah. Yeah. Anyway, so and maybe in the exercises, but you don't have to. Anyway, if you're interested, you could solve that. I mean, you could do that, but they're given to you in the in the actual information sheet. So we've got Maxwell's equations, right? So under the assumption that all fields are harmonic with the same frequency, we can write them all down as this, okay? And we'll just do one, okay, to make sure that you understand how they've come about. So, yeah, equals minus the dt, okay? And we know that E equals the real of this phasor, e to the j omega t. Okay, and say B equals the real of some phasor e to j omega t. Okay, so we have this is going to go to equals this is the time derivative minus dt of e to j omega t. Okay, now this is the temporal part, so it has nothing to do with the spatial derivative here, right? So we can take that outside. Okay, so it's going to go to e j omega t. Okay, and this one we know that this is going to be j omega t minus, and this is just going to be b e to the j omega t, right? And we can get rid of here, yeah, minus. Oh, sorry. Yep, right. Okay, so it's just going to give us minus j omega b. Okay, which is what we've got here. Okay. Okay, so you can go through if you really wanted to. Okay, but okay, and also with b relating to equals mu h and d equals epsilon e and j equals sigma e to bring in materials. Okay, so because of the phasor notation, we managed to get rid of the the time derivative in Maxwell's equations. Okay. Now and we'll do this now. We can actually show that from Maxwell's equations of phasors, we can derive these equations. Okay, we'll do that now. Okay, because it's an important thing. So whenever I've got important good to work through, you should do it. Right. Okay. Okay, so we'll go through and we'll do one of them. So we know that we've got equals minus j omega b. Okay, that's one, and we've got also equals j plus j omega d. Okay, and we know that b equals mu h. Okay, so this one goes to equals minus j omega mu h. Okay, because we'll put that into there. Okay, and we can take cross product of both sides. Okay, so we go. We take the curl of both sides. Sorry, we're going to take the curl of this. Okay, now these are just if it's isotropic media with no boundaries in it, then this mu and epsilon aren't a function of space. Okay, they aren't spatially dependent, so they're just constants everywhere. Okay, so we can take all those constants out. So we're going to have equals minus j omega mu outside of curl of h. Okay, and then we can bring this into there equals minus j omega mu outside of j and d. Okay, and we know that j equals sigma e, and we know that d equals epsilon e. Okay, and so that we get something like this: omega mu. This is going to be sigma e, and then this is going to be minus times minus 1 will be plus omega squared mu epsilon e. Okay. Okay, now this part here, there's one of your vector identities here, okay, which gives that to be equal to, okay. Now, we know that equals rho equals 0 because we've got no free charges, okay. We said that we've got no charges and, no boundaries, okay. No charges, no boundaries. So that means that an E can be taken out because there's no boundaries, so that's epsilon, okay, it's going to be equal to 0, right? So that means that, okay, so that go into there. So this eventually go to just minus, it's going to be equals E outside of omega squared mu epsilon minus j omega mu sigma. Okay, and then we bring that over to the other side and we'd get del squared plus omega squared mu. That's what it's meant to be, and indeed it is. Okay, so that gives this form. Okay, so where this kappa squared is equal to this. Okay. Now we can try and put in so you can see we get that. You can do the similar if you really wanted to with the h. Okay, you can see that E has to satisfy this equation. Okay, in linear isotropic media, E must always satisfy that equation. If you're talking about for harmonic fields, single frequency harmonic field has to satisfy this equation. Now we can try a solution that it's a plane wave, right? So we've got our plane wave here, right? Remember we said that this is a plane wave, and so if E is a plane wave, okay, we can put that into this equation, see what's going to happen. Okay, so we know that this Laplacian given here is going to be that's going to go to minus k dot k e or e naught omega e to the minus j k dot r. Okay, and it's going to be plus omega squared mu epsilon j omega mu sigma E naught omega e to the minus j k dot r, okay, equals 0. Now, if E does not equal 0, right? So if E naught is not 0, so if you don't have a non-zero, so if we had a 0 E field, then that would be true, right? Okay, but if we have a non-zero electric field, which is the case, then it means that, because we can divide through by those, it means that k dot k has to equal, okay, that's what it means. That's what it means this. Okay, so you can see that the real and imaginary parts of the k vector have to be have to satisfy have to be equal to the real and imaginary parts of this kappa squared. Okay, some alternative notation. So this is kappa here, right? Which is found that kappa is given by this, okay, because we just derived that. Okay, k dot k has, which is k dot k. Well, k is the direction. Actually, it's the vector. K dot k, or k is where is it? K is this kr minus kki. Okay, or if it's collinear, it's kr minus jki times the unit vector in the k direction. Okay, that's what k is. Okay, so k dot k is going to be kr squared minus ki squared minus 2j kr dot ki. Okay, and that has to equal this kappa squared, which is this. Okay. So E naught is unrestricted magnitude and also direction. So we haven't said much about E naught. It's a vector. Okay, we're going to see that it has to be a transverse wave. Okay, the requirement that the wave has to be transverse comes from that we've said that there's no free charges and no boundaries. Okay, and then the divergence of E has to equal 0. Okay, so if we take the divergence of this, okay, why is this suddenly turned off? Yeah, there we go. The divergence of this, if E is of this form that we said is a plane wave, okay, that's just going to be, you can see from your formula sheet, it's going to be minus j k dot E times the E phasor again, okay, and that has to equal 0. Okay, now it could be that that's true if E is 0. Okay, if E is 0, that'd be true, or if K was 0, that'd be true. But it also, so there's like the trivial solutions, but it'd be true if K dot E is 0. Okay, and K dot E would occur if the E field vector is perpendicular to the K vector. Okay, so if you think of K vector as the direction of propagation, then it means that the E field is perpendicular to that, so it's transverse. Okay, it's a transverse wave. Okay, so E naught is orthogonal to direction of propagation K. Okay, and the similar, also we can put in the curl of, we can find what H is from the curl of E, right? And when we do that, we see that when we find the curl of E, we see it's K, turns out to be K cross product with E. Okay, and that's going to be equal to H. So we know that the cross product of K and E is going to be perpendicular to both K and E, right? Okay, so if this is direction of propagation, you might have E here at 90 degrees to that, you're going to have H, but it's also 90 degrees to K as well. Okay, so they're transverse magnetic waves. Okay, so is that clear? They're transverse magnetic waves. They're orthogonal. Okay, so the transverse magnetic waves. How much time we got? Sorry, the E and H, the transverse magnetic waves, propagating in the K direction. Okay, E is the E field, E is the electric field, and H is the magnetic field. So, okay, it's good that you guys are here. Maybe it helps me explain it better, because I understand it's conceptually not that easy, right? Yeah, it's good to explain it through maths, right? Oh, you want a video? Yeah, I don't know. I mean, cartoons. You should do the maths, and then you can see. It should become clear from the maths. That's the actual description. Okay. So we can also define this Ki to be alpha and this Kr to be beta. And you also get some of this in the formula sheet, right? But just be a little bit careful of the definitions, of because you've got gamma here. Okay, but you do get some of this stuff here. Okay. So you can we can see that by equating the real and imaginary parts of the two sides of the equation, okay, we could find isolate what alpha and beta are. Okay, so you could have you see that if you would multiply this out, you'd get beta squared minus alpha squared has to equal omega squared psi mu, and then it's also here minus 2 alpha beta times j, right? Yeah, it's going to be equal to minus j omega sigma mu. Okay. So that says that alpha is going to be omega sigma mu divided by 2 beta, and you can put that into there. Okay, you get beta squared equals omega squared sigma squared mu squared 4 beta squared minus equals omega squared psi mu. Okay, and then you get 4 beta to the 4 minus omega squared sigma squared mu squared minus 4 beta squared omega squared epsilon mu equals 0, right? And that's a quadratic in beta squared, right? You can solve that, okay? And you eventually end up with these solutions, okay? Yeah, sorry about that. So that's how you could do it, right? You don't have to do it, right? Don't worry too much, right? But, you know, you can get these alpha and betas, okay? Okay, so we're doing that. Almost at the end. So an example is an E field polarized in the Z direction and propagation in Y directions. Okay, then we've got alpha equals alpha times the unit vector in the Y direction, beta equals beta times the unit vector in the Y direction. Okay, then we put that in, and then the actual real field would be some constant vector. Okay, times well, we put it in the AZ direction, constant times AZ. Okay, e to the minus alpha times Y. Okay, alpha is a function of omega as well. Okay, beta is also a function of omega. Okay, times cos omega t minus beta times y. Okay, so it's a plane wave that's decaying by factor alpha, e to the minus alpha times y, as it heads off in the y direction. Okay, and that's the attenuation. This is related to the speed, it's related to the phase velocity. Okay, remember the phase velocity is given by, I think, beta divided by omega. Okay, just remember we had that before. We had when we looked at waves. Okay. Waves are attenuated, they propagate and diminish to 1 on E of the values in a distance of 1 alpha meters. Okay, a uniform plane wave is talking about the impedance. Okay, because you know what H relationship between H naught and E naught. You can work through that if you want. Okay, more interesting is look at as these waves propagate through various types of linear isotopic media. Okay, so remember we talked about we could have insulators and conductors. Okay? Now in a good insulator, sigma equals 0, right? You don't have any conductivity. Okay, so and you were saying at the moment that this epsilon mu, so mu is mu naught. Okay, that's typical for most insulators. Okay, and then epsilon equals epsilon r, epsilon naught. Okay, the important thing is sigma equals 0, so this is going to be 0 here, right? Okay, so this alpha turns out if you put root of 1 plus 0 is 1, minus 1 is 0, equals 0, right? So it's not attenuated. So when a plane wave goes through an insulator, you're not going to get attenuation. Okay, if it's a proper good insulator at that frequency. So that's why light goes through air, a little bit of attenuation, but that's because there's some absorption that's not, but very little, right? It goes through glass, it's an insulator, right? Okay, that's why it goes through. And the unattenuated the waves are unattenuated and propagate with a phase velocity, which is omega divided by beta. Okay, which is c divided by the square root of epsilon r. So phase velocity. We only deal with the phase velocity here. Okay, and it's given by omega divided by beta. Remember, beta can be a function of omega, right? Beta is going to be omega squared. What's it going to be? Beta squared will be omega squared times. So beta will be omega times the square root of epsilon mu. Okay, and this we only take the positive square roots of these equations here, okay, because the materials we deal with are fairly natural materials, and we're just going, for the moment, we'll take positive square roots. But then, so you could see that omega divided by beta is going to be basically just 1 on the square root of epsilon mu, okay, and so that's where you get. We know 1 on square root of epsilon naught mu naught c, speed of light in vacuum, okay. So that's where that comes from. Okay? Sorry, that's all here, isn't it? Put it down. Okay. Now, a more interesting propagation in a conductor. So also a very good example to work through. Okay. So in this case, alpha does not equal 0. Okay. We've got two situations. Okay. We could have a good conductor, a reasonable conductor, would be remember we looked at the displacement current versus the conduction current before. I think. Okay. So remember we said if we've got a good conductor, then sigma is high. Okay. Okay, is large. Okay. So omega in that case, and if the frequencies aren't too high, then we'd have omega much less than sigma on epsilon naught, okay? Because epsilon naught's a really small number, right? It's